Hi, hello. What we're going to do today is we're going to talk about the exponential of a matrix. I am going to try to have a decent level of rigor. The matrices involved will be matrices of real numbers. I'm not going to be dealing with the more abstract algebra versions of this. So, and basically, in order to follow along, you basically need to know a little bit of linear algebra and your results involving series and infinite series at the level of calculus 2. So let's get started. And first of all, let's talk about what the definition of an exponential of a matrix is. The definition is usually written e to the a, where a is a square matrix. And that's how it's usually denoted. The actual definition, and hold on, I want to turn off the lights to get rid of the glare, but the actual definition would be as a series. And if you remember the series expansion for e to the x, remember e to the x as a series is 1 plus x squared over 2 factorial. For real numbers, well, the analog for e to the a would be the identity matrix, same size, plus a squared over 2 factorial, and this makes sense, and so on. Now, the very first thing we have to worry about is that if we talk about this infinite sum, what we could do is we could say, well, let's define SK to be this. Where k is a positive integer. Now, clearly, this is well defined. Because it's just a finite sum of well-defined matrices. And we'd like to be able to say e to the a would be some sort of limit as k goes to infinity of sk, the usual definition for a limit of a series. However, we are working with matrices. So if e to the a is going to be a matrix, e to the a can be defined by its entries. So basically what you'd be saying is let e to the a be the matrix whose aij entry, so in fact, let's call it this, its ijth entry is a limit as k goes to infinity of the ij entry of sk. Now, this is pretty abstract as it sits. So let's take a quick break and do a couple of examples so you get a feel for what these things might look like. Now, note, in general, e to the a can be hard to calculate directly. And of course, I have to show you that this idea here, that this limit in fact exists, and I'll be doing that shortly. But in order to do that, let's go ahead and do a couple of examples. And one example I'd like to do, let's start off with an easy one. Example. It's not very good writing. let's say let A equal, let's do load 2 by 2s. Let this be, let's say 2, 0, 0, 4, just for grins, okay? Well then, it's easy to see that A squared is just going to be 2 squared, 0, 0, 4 squared, and A to the K, again, it's just direct computation. So for a diagonal matrix, it's not too bad, right? So now, we want to take E to the A. That's just going to be I plus 2, 0, 0, 4, 2 squared, 0, 0, 4 squared, and so on. And I put some ellipses here. 2 to the K, 0, 0, 4 to the K, and so on. So now, what we see immediately is that if we look at the first row, second column entry, that's clearly 0, as is the second row, first column, the off diagonals. It's very easy to see because you're just adding a series of zeros. On the other hand, the 1 term would be 2, would be 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial. We recognize that right away, right? That's just nothing more than the series for E squared. And similarly, plus 4 squared over 2 factorial, etc. So this, because it's, it goes on, that's just E to the 4. Okay? So it follows just from, from a little bit of algebra that this E to the A is just going to be the matrix E squared, 0, 0, E to the 4th. Okay? Okay, so that's what these things look like, and that's sort of an easy one there. So that basically gives, now let's look at a second one, a second example. If we look at, let's say, B equal the following matrix, then with a little bit of calculation, you can see that B squared is going to be the negative of the identity matrix, and just work it out. Just multiply B by itself, and you'll see that. B cubed is just, of course, going to be the negative of B. And B to the 4th equals the identity. And again, the beginner is going to have to probably work and show these things, but none of them are bad. So now if you want to talk about E to the B, you have I plus B minus I over 2 factorial minus B over 3 factorial plus I over 4 factorial. And this whole pattern repeats itself. B minus I minus B, I, etc. All right. So we'll go ahead and we'll look at that for a second. And let's finish this up. This isn't too bad because if we look at the first term, the first row, first column term, it starts with a 1. That's a 0 because it's a b. Then it goes to minus 1 over 2 factorial. That gets skipped. Plus 1 over 4 factorial. And then the pattern goes on. Okay? And notice the way this works. This is also going to be the off diagonal. I mean, not diagonal, but the second one is the same. These are the same right here. Okay? Well, in fact, you've probably recognized this. 1 minus 1 over 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial. Think about the Taylor series. That's just the Taylor series for cosine of 1 radian. All right? Now, if we look at ED, first row, second column, that starts off with a negative. That starts off with a 0 for the I. Then it goes to the negative 1. Right? Then it gets skipped. Then negative b gives a positive 1, so it's going to be plus 1 over 3 factorial minus 1 over 5 factorial plus 1 over 7 factorial. And we know what that is, right? That's going to be negative sine of 1. And similarly, to 1, we're starting with a 1 here. And the signs change this way. So this thing here, e to the b, turns out to be cosine 1 minus sine 1, sine 1, cosine 1. Okay, that turns out to be important for the subject to differential equations. So that's what these are. These things are in fact are matrices of the same size. And here convergence was no problem. But we don't always know. I mean, how do we know in general we're going to get something? Well, here's the deal. In order to actually make sense of this, and then what I'm going to do is I'm going to work at a coordinate level like this. I'm going to go ahead and show you a couple of things. There are many ways to do this, and probably the easiest way to do this is to talk about the norm of a matrix. Now, the one I'm going to use is the most convenient for this. And the norm of the matrix I'm going to talk about, I want to talk about the norm of A is going to be a sum over all its entries of the absolute values of its entries. For example, the norm of the 2 by 2, 1 minus 3, 0, root 2 would be 1 plus 3 plus root 2. You just take the absolute value of each entry and add them up. I don't want to get into the theory of norms or things like that. But what I do want to point out, and I think this is an important thing to do, is the first thing is that the norm of A is greater than or equal to the absolute value of any one of its entries for all ij that work. So the norm of A definitely dominates the absolute value of any of its entries, and that's pretty easy to see. And the second thing I think it's important that if you take the norm of A times another matrix B that's also square, that's going to be less than or equal to this. Now, I'm not going to give a full-fledged proof of this, but I want to express why it's true. For 2 by 2s, and here's how you can see it. The norm, think about A11, A row 1, column 2, A21, A22. And let's say you multiply by this. And then you take the norm. Well, what products do you get? You have A11, B11, then you're going to take the absolute value. You're going to get, well, not yet. You're not going to take the absolute value yet, my bad. Plus A12 times B21. So notice this A11 is going to be multiplied by that. And now you're going to take the absolute value. And then let's look at the next one. A11, B12. The ones have to match. The 2's have to match. So remember, these things have to match. And then we get the same thing on the bottom. So all I'm doing is matricing and multiplying the matrices. So it's A21, B12 plus A22, B22. Now, you might not, say, okay, big deal. That's what the norm of this is. But here's the key thing to notice. Notice A11 gets multiplied by B11 and B12. It doesn't appear anywhere else. A12 gets multiplied by B21 and B22. That's by the way you multiply matrices, right? This thing here is going to match with this. This thing here will match with that. Okay? Now, let's just move this to the side. And we're just about done with this little tidbit here. If we now just look at a matrix A times matrix B, well, the norm of matrix A is this. Remember, you take the absolute values of this. And that's multiplied by, and I'll just scroll down here. Absolute value, absolute value. And then what do you notice? The A11 gets multiplied by all of these, not just the B11 and the B12, but it gets multiplied by every single one of these. The A12 gets multiplied by every single one of these, not just the B21 and the B22s, and so forth. So here, every entry, every Aij gets multiplied by all Bij, not just select ones. So you have every product that you have here as an absolute value, and you have more products, more additions of possibly positive and or non-negative numbers. So in fact, this is fairly clear. So then what that basically tells you, and this is, I'm going to call this 2 prime, this tells you that A, and if you raise it to the kth power, it's going to be less than or equal to A norm raised to the k power. And this is what we want right here, this thing here, okay? So in fact, now that we have this thing, we can return to our original goal is to make sense of the exponential of a matrix. So let's start with this. So let's start with a realization. So from this right here, from 2, we get the following important result. I think it's important anyway. And what it says, what 2 says, that I'm going to call this, let aij to the kth be the ijth entry of a k. This is not raised to the k power. The k is being used as a superscript here, not a power. So superscript, not power. And what this basically says is that this aij k, the kth entry, is going to be less than or equal to the norm of this, but it's also going to be less than or equal to the entire norm to the k power. And this is the inequality that I really want right here. So remember, this is the ijth entry for a k, right? And we have that completely dominated by this. Now we're about ready to seal the deal. So now let's take a look at this. Let's take a look at e to the a, and let's look at its ijth entry. Well, its ijth entry is going to be the ijth entry for I plus, that kind of looks like I, so ij, plus the ijth entry for a plus a squared ijth entry over 2 factorial plus a 3 over the ijth entry, etc., right? Well, by what we said right here, by this little thing, this is going to be less than or equal to this series. What I'd like to do is I'd like to show that, let's show the series is absolutely convergent. Well, we know that from this part right here, if we just look at the absolute values now, so I'm just slapping absolute values here. That's less than or equal to the norm of I plus a squared over 2 factorial plus a cubed over 3 factorial plus etc., which is less than or equal to by this. And again, I know you have to go out to k and then do a limit, but I think those straightforward steps follow pretty easily. And here's a key step. That's absolute a squared plus absolute a cubed and this series here, by the series for e, this is just e to the absolute a as a real number. So this series of positive terms is bounded by an absolute convergent series. So what that basically says by series comparison we'll just close it up here. By series comparison, the series for e to the a ij absolute is absolutely convergent. because remember, that's a series. So this right here is convergent. So that actually proves the fact that our series for E to A converges. And thanks for listening.